It's kind of slow. We won't do anything for a while. Yeah.
I had a question about, was it my degree works?
Oh, yeah, okay, that's a weird thing.
Yeah. So I was just wondering if you knew, so I need one more technical elective,
Uh-huh.
but I'm also a nuclear associate, and I still need radiation health physics. So will they work
Yeah.
together?
Yeah.
They will?
Yeah.
So in that case, because I have myself taking radiation health physics and alternate energy systems to get the technical elective and radiation health, so I don't have to take alternate energy systems then?
Okay, wait a minute.
I can show
Is
you.
it an engineering or technical elective you need?
I think it's an engineering elective.
Well, if it's engineering, it'll work.
Okay.
But if it's technical, okay, okay.
Yeah.
Here's
yeah.
the deal. If you've got enough for that your engineering electives are covered,
Yeah.
then what you need to do is talk to Crone, and it's possible. Here, I need to cut off the microphone because this is a. Here, hang on a second.
Okay, that's fine. I just.
So I got kind of conflicting signals about when. So initially they published the final schedule as one thing,
Yeah.
and then it got switched to something else. So my question is kind of, what's the current final schedule? And here, let's do this. Here's the exam schedule. So it can't be that it would be different than that. So here, if you look at the exam schedule, it says blah, 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 lots of blah, blah, blahs. But it looks like it's December 2nd, 3rd, 4th, 5th, 3rd. Oh, okay, that must be Monday and Tuesday. So I think I did it. Okay, now wait a minute. Okay, so that's online classes. I went ahead and did it for the 7th.
Okay.
But I may move the midterm back a few days.
I was afraid that it was due like this week or next week for midterm stuff.
No, what I'm gonna do, I mean, I'm trying to be flexible because I don't know what's going on. I think the cases are getting better, but I want to kind of try to be reasonable. But at the same time, what I'm gonna start doing near the end of this week is sending out weekly mails that has, okay, here's your status, here's what you haven't completed, here's what you need to complete.
Mm-hmm.
And that'll help people realize, oh, I guess I better get doing something. So, okay. Let me see if I can find the fluids. I think, okay. So have y'all made your way through Bernoulli's stuff yet?
What section is that, you know?
Let's see, it can't be this, but I might be wrong. It might be that. Oh, it is 3. Okay, so have you made your way through that one? I mean, I can do a problem or two, or I could tell you what I could do. I could go straight to the Blackboard site and address the problems that you actually have assigned. But oh no, don't make me do that. Oh, thank you. This is this fall. This is, there it is. Go all the way down. I don't know where I put this at, so let me just hit 7. No, that's not it. That's the curved gates. Did y'all get through the curved gates? Okay. Okay, so let's see. That is 7. Content 8. Yeah, there's Bernoulli's equation. Let me go to the bottom. Look at this one. Here, I'll just do a quick rundown on, I think that, let me see if this works. Oh, it does. Okay, now how do I erase? Oh, good. So what I'm going to do is instead of copying this over to OneNote, okay, I'm going to write on this. It'll disappear when I'm done, but, you know, hey, this might work pretty good. Okay, so let me just give you a rundown on each one of these. Of course, there's 1. He's identified 1, and he's identified 2. The facts you know at 1, of course, here's one fact you know at 1, and here's another fact you know at 2. So if you look at Bernoulli's equation, it looks, okay, so the ink, I can't change the thickness of the ink here. So if you write it like a civil engineer, I'm trying to write slow, but it seems to catch up. You actually have 3 things to know. Let me write it and then put the subscripts after I finish. Okay, so 1, 1, 1, 2, 2, 2. So you only have, and so this is one thing that's kind of helpful, for me at least, and actually I've heard other people say the same thing. If you make a table, and then let's say you have, now in this case we don't, but you could have, say you had 4 points in there, and we'll run across one, maybe I gave one where there's that much. And if you start looking at it, number one, or location one, in other words, you do know the pressure there. Oh, he tells you water flows from it with a velocity of 15. So you do know that one. And you do know that one. At 2, you do know the pressure. You do know the velocity, actually, but you don't know that. So in actuality, you've got one equation and one unknown. What you know about 2 is the velocity sitting here at the top is like it's bubbling around, and it's not going up or down. It kind of goes off like this. So you got that, you got this, you got that. Both pressures are outside and exposed to the atmosphere. That's supposed to be a 2. It looks like a 2. You have that. So essentially you have Bernoulli's equations where you know this. That's the P1 at the time. You know that. You know Z1 because you've made your datum right here, and that's going up. You don't know, but he told you this one. And you wouldn't ordinarily know that, except that somebody told you that. And you do know that. And so the only thing you don't know is this one, which is how high this thing bubbles up to. This is a pretty standard problem because it's essentially a fountain. How high does your fountain go? And that's pretty much it. What does this thing do? If I click that, what is that? Is that an eraser or is it a highlighter? Oh yeah, you're right. Okay. And there's some dots right there. Oh, calligraphy pen. Oh, a crayon. Oh, that's funny. We'll just stick with a pen. I didn't know it had that. And then they got other things here too. Now I can't get it to go away. There you go. Can I just go to the next page? Oh, it gets stuck on the screen. Okay, so I've got to erase it. It does have an eraser here. Okay, so I'll go to the next page with a clean slate. So this one's a funny one. Let's overdo it. What I mean by overdoing it is this. So he identifies 1 and 2. I'm going to over-identify it and say 3. And again, you could do Bernoulli's like this way, or you can do this. So both of these are the same. I'll say that's a constant 1, and this is a constant 2. But it turns out the only difference is you just multiply the top equation times gamma, and you get the bottom equation. So you can do either one. But the key is, in either case, you'll have to know P, V, and Z. And you've got 1 and 2 and 3. So it's kind of helpful to kind of make this table right off to see what it is you have to do. Okay, so I haven't even read the problem yet. I know it's the section on Bernoulli's equation, so I know I'm dealing with Bernoulli's equation. So then it says the water flows from the pressurized tank through a 6-inch diameter pipe, exits from the 2-inch diameter nozzle right there, and rises 20 feet above the tank, above the nozzle. Determine the pressure in the tank if the flow is steady, frictionless, and incompressible. Frictionless means there's no losses. So I can use this Bernoulli's equation. So let's start hitting this thing. Okay, so what do I know? I actually know, so I'll do the pressures, then the velocities, then the C's. So I do know the pressure at 3 and 2. Now I've put an artificial point here, but sometimes it's beneficial to have extra ones. And the pressure at both 3 and 2 equals 0 here and here, because it's on the outside, or atmosphere. Pressure at 1, I don't know, that's one of the things he wants to know. Velocity, actually, you do know the velocity at 1. So you make this assumption that this tank is really, really, really big compared to the 2 inches. If you do, it moves really, 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 really slow as it drains the tank. So here's your tank, and the level of water is draining really slow. Let's say it's 0.01 feet per second. Now, take that and look in the Bernoulli's equation, and you realize you're squaring it, so that term becomes that big, and it becomes less and less significant. So you can pretty much assume that the velocity 1 is 0, and you're okay with that. Velocity 2, I don't know. Velocity 3, I do know. Velocity 3, no, I'm sorry, 2, I said that wrong. So 3, I don't know. How do I erase? If I put that there, hey, what's going on? It won't erase. Anyway, scratch that. I can't erase for some reason. Uh-oh. I've messed up somehow. What's that do? It's the eraser. Well, I goofed it up somehow. We'll fix it in a second. So then the next question is, what about Z? That's a good question. As I see the top of the water at 1, let's see, the water flow through a 6-inch diameter, exits a 2-inch diameter, and rises 20 foot above the nozzle. Determine the pressure in the tank if it's steady. That's interesting because you really need to know the level of that water. In other words, you need to know, in each of these cases, you're going to have a datum. So legally, unless you assume that water is at the same height as this top, if you don't, I mean, that's going to be problematic to determine that. So, velocity at 2. I didn't need to know that. Height at 1. I see that as a problem, so I'm going to do PROB. Height at 2. If you set your datum at the top, you'll know that and you'll know that. So then your question is, how do you solve this? I'm seeing this as being a little bit of a problematic situation here. Water flows from the pressurized tank through a 6-inch diameter, that's fine, exits from a 2-inch diameter nozzle, and rises 20 foot above it as shown. Determine the pressure in the tank if the flow is, that's fine, but there is something missing there, and that's the height of that water relative to the top of the thing. Now here's, oh, yeah, I gotta get, how do I get rid of this thing? Eraser, is this, no, that's,
I think the eraser still works, I think you just have to, you can't just tap it, and you have to actually move.
oh, really? Oh. Oh, okay. Okay.
I think we worked with this in high school, and,
Oh, really?
yeah, we kept trying to like tap it in, just didn't work, they had to actually move it.
Oh, okay. Let's do this because this is annoying to me. Okay, so first, let's get this. Okay, so first, let me write down and see what he says. He says pressure 1 is that. Okay, I don't know how he arrives at some of this, but I'm going to first, given the information, I'm going to work between this spot 3 and 2. P3 over gamma plus Z3 plus V3 squared over 2. Do I put the G? Usually I put the G after, but anyway. V2 squared over 2. I'm not organizing this. Okay. Sorry about that. I interchanged values around. So the P3 and 2, they're not there. If I set the datum here, then this 0 and this is 20. If V3 is something, but V2 would be 0. So what you would have is V3 squared over 2G is equal to 20, or V3 is equal to 2GH square root. Now take a look at that for a minute and you'll see, you'll think to yourself, hey, wait a minute, that looks familiar somewhere in my history. Now H is that 20. Think of this being H. So imagine if you flung a marble straight up and then it reached the top of its path and is about to come back down. So if you're doing that, your kinetic energy is 1/2 mv squared equal to the potential energy mgh. M's cancel. Take the half over and you get v squared is equal to square root of 2gh. Remember we were talking earlier that this is nothing more than an energy equation. So suddenly you start to see the evidence of that because, so what's that tell you? It tells you V3. Hang on, let me get this. I'll go ahead and take it out of there. Okay, once you have V3, technically, you do have to know that elevation. Now you can assume what you want to, that's fine, but that doesn't mean it's the correct assumption. So, here, I'll make myself some extra space. So what we find out is V at the exit, or V at 3, is equal to square root of 2GH, or 32.2. H was 20 feet. That's going to be the velocity at this exit right here. It really doesn't matter because you still have to come back and say this. Now, it may not amount to much. P1 over gamma plus Z1 plus V1 squared over 2 is equal to. Now, you can write it all the way to the top or it doesn't. Doesn't matter. You can write it from P2, Z2 plus V2 squared over 2G, or you can write it from P3, Z3 plus V3 squared over 2G. The fact of the matter is, you've got to know this distance. So I'm just going to make it up and say that this distance is going to be D. And what I'm going to do now, I'm going to write between 1 and 2. And so I'm gonna forget 3, and I know I found 3, but I'm gonna forget it for a minute. Because I know the pressure at 2, the velocity at 2 are 0. So this, if I make this datum sit right here, then Z1 would equal 0, but Z2 would equal to, equal to 20 plus whatever that little distance is. Okay? Sorry about that. But then the question comes up and says, okay, what is the velocity of this face as we're draining? Very small, so it's going to go out to nothing. So then what we're going to see is we're going to say P1 is equal to gamma. Okay, so the only terms I got left that are not 0 is that one and that one. Gamma 20 plus D. This is really unfair because you really need to know that D, but assume the D is tiny. I don't know. Gamma is 62.4, and if it's 20, I mean, I hate that. What's 62.4 times 20?
1248.
Yeah, so there's a little bit of a problem with this problem, and that is that there's geometrically, it's not exactly correct because he's assuming that this water is at the same height as here, but he hasn't drawn it that way. And so technically that D needs to be in there. Say it's a foot. If it's in there a foot, then it's 21 foot. Hey, where did the thing go? There it is. I can scroll. There it is. So if it's 21 foot, then it's bigger than 1248. So I'm not criticizing or saying that 62.4 times 21 foot would be 1310. So he's drawn something and he's made you work something. And I'm not saying he's incorrect, but his drawing doesn't match what the numbers are. To me, there's a D in between there. There's a distance right there.
Maybe, because we have a bunch of stuff with diameter, like it's a 6-inch diameter pipe that goes into a 2-inch diameter pipe.
Uh-huh.
We didn't do anything with that.
Yeah, it's just, I think now this happens a lot with these problems where somebody drew it and then the addition changes and the picture will change occasionally. This book dates back to the 80s, 1980. So, and this is it's in the, okay, is it in the 8th edition or is it in the 9th? It's either the 8th or 9th edition. I can't remember. I vividly remember the 8th edition cover. But I think they did come out with the 9th edition and I can't. And so what's funny is there'll be a problem, it'll disappear and it'll reappear like, a few editions later. So it's a grand shuffling of a deck of cards. So hate that, but if you're being meticulous, those need to be drawn at the same height. Oh well.
It even says air up above the water, so it's like, you assume it's full and there shouldn't be air, but
Yeah.
the figure says air.
Yeah, so maybe the way this picture should be drawn is kind of I can't really, it should be that this part goes up higher and then there's a little thing and then the water level should come to right there. And then this should say air. Then that's legal. And then that would be the same height as that. That's what it should be. Or, this little nozzle needs to be dropped down. I don't know. I don't know. But the fact of the matter is, the way it's drawn is if you're writing Bernoulli's equation between here and here, you've climbed that distance, not that distance. So, yeah, these are intricacies that happen on some of these problems. Let's see, this one is not as, it doesn't have any height issues. There's no height issues here. So in this one, it's just kind of straightforward. You got a 1, he's already identified 1 and 2 for you. 1 gamma plus C1 plus V1 squared over 2G equals to P2 over gamma plus Z2 plus V2 squared over 2G. So then you have to identify things. Well, first, the elevations are the same. So you can just X those out. The next thing you got is, the diameter's changed. So what you got is A1V1 is equal to A2V2. Now, he gave you diameters and not areas, but and it says diameter, so I'm assuming that the pi, well, I guess if he gave you diameter, you do pi d squared over 4, so you get pi d1 squared over 4, v1 equals to pi d2 squared over 4, v2, pi's cancel, 4's cancel. So what you get is d1 squared v1 is equal to d2 squared v2. You can either or scratch that out, say v1 is equal to that, plug the v1 in here as being v2, but d2 over d1 squared, but you didn't have to remember that it itself is squared, so it becomes a 4th. Then, let's see what else he says. The nozzle must be capable of, 250 gallons per minute. If the nozzle is attached to a 3-inch diameter hose right back here. So the pressure 2 at the exit's nothing. So it's squirting out onto the ground, I guess, or up against the building. Okay, so if it's 250 gallons per minute, then a gallon is kind of a volume measure. So 250 gallons per minute, and so many minutes in 60 seconds. I don't know how many gallons are in a cubic foot, but I think it's 7.4 or 7.48 or 7.5 or something like that. And so you can convert this to cubic feet per second. Then the cubic feet per second is the same exact thing as that. There is no difference between cubic feet. You can change that to this. Once you've got that, you can turn around and get V1 and V2. The only thing you don't have is the P1. So since he gave you the flow rate and the volumetric flow rate, you can turn around and extract out V1 and you can extract out V2, put them in, everything else is clear, and you get P1 out of it. So that's a little bit more straightforward. So in this you use continuity, and you use Bernoulli's. And in the continuity, you have this term too. So you have this goes embedded in the continuity there. That tells you your V1 and your V2. It doesn't tell you. I mean, you gotta, oh geez, you gotta calculate it. You know what? I did not check the stream here. Let me check it real quick. Of course, it's kind of too late now. Okay. Hopefully it went off without a hitch. Oh, it looks like it's going. You know what? I did not check the
Oh, there we go. There it is. I see the same, oh, I see the screen is just a few seconds behind what the screen I have here is.
So, all right, so what's the next one? Well, that's it. Did I only give 2? No, there's a third one. No, I did 3. Oh, I should have given more. But I'm not going to go back and add them. Okay. Okay, so let's hit whatever the next section is. This is the content for 8. Let's hit the content for 9. Wait,
Eight and nine.
yeah. Well, wait a minute. That was. Okay. You know, I think I was having, that was the week that I set everything up and I had midterms running. So that's why I combined those. Okay, so let's see, 8, 9, 10. This is the sum of the forces, the momentum thing. So, okay, let's hit the first one. Okay, why is it not going up? Come on, there you go. So there's a lot of junk in these. Okay, so it says determine the anchoring force required to hold in place the conical section attached to the end of the lavatory faucet shown in the figure. So to me, it looks like it's only in the Z direction. Well, you know what? Let's call this the Y direction. And we'll make this positive. So the way this works is you do the sum over sum of the forces, and in this case we only have Y, is equal to the sum over the control surfaces of Vy, because these indices have to match, V dot N area. So believe it or not, that's the M dot with the positive out and negative in. The reason it's positive out and negative in is, let's say you put the surface right here. Normal points out, velocity goes in. Dot between those two means that the inlet has a minus sign. Does he give us, oh, well, okay, there you go. He gives us that. He tells us it's water. So what I'm getting, oh, I forgot the row right there. Sorry. So what we have is, okay, V dot N area, that will essentially be translatable to the 10 gallons per minute, but you'll have to change that to cubic feet per second. Okay, then you have density. Well, the density of water is 1.94 slugs per cubic foot. And then what you got is just Vy. So in this particular case, it looks like the water's flowing down. So if I take this to be positive, then I have to do it the same on both sides. And so what I have, does he label them 1 and 2? Oh, he does. here's 1, and here's 2. So in section 1, his velocity, it's hard for me to see, but his velocity on both sections is going to be going down or minus. So as long as you keep up with that and keep the signs, I guess here, usually in statics they'll have that. So then you have the anchoring force, the weight of the water. Well, he says the weight of the nozzle too. Then you got, this is the one area, you got pressure times area, and then you got pressure times area here. So these little vectors in the middle are all your forces right there. So if you just add them up, okay, so I have to be careful because I've designated up to be positive. So I'm going to go from the bottom to the top. Oh, yeah, weight of the nozzle, weight of the water, force anchoring. I'm having a little trouble reading this thing. Minus P1A1. So I took care of this one, then I took care of that 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 one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then I've got my inlet and my exit. So now I got all this crap in the way. Then let's go back. So I don't know which one to do first, the inlet or the exit. I do the exit first because the exit goes out. Okay, the velocity at the exit is going in the minus direction. And I'm just going to say E because the velocity of the exit can be determined from the fact that rho, or I could say VA, has got to be equal to 10 gallons per minute. And so I can get the area down here and get the velocity out of it. So I'm going to say that. Now, in the exit, it's going out, so I'd say positive. Then I'd say V inlet because it's coming in, but it's still going down in the minus direction. But the M dot there is positive, and those M dots are the same. And that's it. Now the question is, okay, the nozzle inlet exit, okay, determine the anchoring force required. Okay, that's what you're trying to find. So he's got to give you this and this. The section 1 pressure, he gave you this. I think he's going to tell you the exit pressure is 0. Yeah, so I think the exit pressure is 0 here. And you got the weight of the thing. Do you see the weight? Okay, the nozzle weight. And then you got to have the volume of water in there, but I don't see, does he tell you how much water is there? I don't see that. So there may not be a, so in essence, you should know everything on the right-hand side. You should know everything with the check. You don't know that one. And that's what you solve for. And so, I'll come back to this section. I need to come back in a little bit more detail. And maybe what I'll do is, maybe I'll come up with a lecture middle or end of the week and send everybody invite to it. And we'll do one, I don't know, maybe we'll do one Wednesday or we'll do one Friday. Maybe, I don't know. I could do one Wednesday from right here. So apparently they want to get in here. So I'm going to let them.